So now that we've talked about alkane hydrocarbons, we're going to move on, sticking with carbon and hydrogen, but now adding in double and triple bonds. And so, as I just said, alkanes we've seen are saturated, meaning putting on as many hydrogens as possible. Alkene means double bond. Alkenes have a double bond. They're unsaturated because they contain carbon-carbon multiple bonds. Same situation with alkynes. They have a carbon-carbon triple bond. So alkenes and alkynes are very useful molecules. They're very useful as starting materials. At the end of chapter 13, we'll talk a lot about different reactions that alkenes and alkynes can undergo. But a lot of organic chemicals, a lot of starting materials for pharmaceuticals, explosive, paints, plastics, they all start with various alkenes. Ethylene is a very popular alkene. More than 28 million tons of it were used to make polyethylene plastic. We'll talk about how to make polymers in making plastics later in chapter 13. Ethylene is also a naturally produced hormone in plants. All right, so step one, we want to learn how can we name alkenes and alkynes. And the process is exactly the same as that we went through for alkanes, with just a couple of twists. So step one, again, just as before, we're going to name the parent compound, meaning we're going to look at the chain, we're going to find the longest continuous carbon chain. Except this time, because we have functionality in there, we have somewhere either a double bond or a triple bond, we have to make sure that our longest chain includes that double or triple bond. We're going to see situations where you can have more than one double or triple bond, and we'll talk about how to name those compounds as well. But step one, exactly the same. Find the longest chain. Just make sure the longest chain includes the double or the triple bond. So you can see here, right, this molecule, the first one up here, we have 1, 2, 3, 4, 5. It's an unbranched alkene. There's 5 carbons. Remember, 5 is pent. But instead of ending in ANE, now we're going to end the molecule in ENE because we're talking about a pentene. We usually have to indicate with a number where the double bond is located unless the double bond is on the first carbon. So now when we start numbering and we're thinking about substituents, and again, we're going to work a lot of examples of these, your double bond is always going to get the lowest number, or your triple bond. Whatever functionality is in the molecule gets the lowest number. Substituents come second. Same situation with the next molecule down. It has a triple bond in there. This would be, it says it's named as hexyne. It would be technically 1,2-hexyne. You would indicate the number of where the triple bond was located. So when you get into some branch structures like this and you're trying to find the longest chain, again, remember, your longest chain needs to include the double bond. So you would have to, in that situation, go this way. You couldn't snake around and go in this direction, even though it's longer, because you would exclude that double bond from the longest chain. Okay, so we found our longest chain that includes our double or triple bond. And like I said, then you're going to have to number the chain, giving your double bond or triple bond the lowest number. So in this situation for the molecule here, we would go right to left because the double bond would get a 2. In this situation, we would go left to right, and again, left to right with this molecule in order to give those the lowest possible number. So while we're on the topics of alkenes and alkynes, cycloalkenes are very common in nature. You will never see a cycloalkyne. Right? So try to draw a cycloalkyne. It will require carbon to form more than 4 bonds. So you'll never see a cycloalkyne, but cycloalkenes will also work on the nomenclature of those. Again, whereas before when we had a cycloalkane, we were trying to come up with a numbering system. We were giving our substituent that had the earliest alphabetical letter the lowest number. Now we're going to give the double bond the lowest number. So part of the double bond is going to have to be number 1. how you pass through the double bond then depends on the rest of the substituents on the ring. So if you're looking here, you've got this cyclohexene molecule, and again, we're going to practice a lot of these. You're trying to figure out how to number this ring. You have to start the double bond with 1. You could either start here where they've shown it, or in the next example you can see it goes here. It has to pass through the double bond 1, 2. You can't go 1, 2, or 1, 1, 2. It has to pass through the double bond 1, 2. But how you pass it through, whether you go counterclockwise, as shown here, or you go clockwise, you can do either. In this situation, you would go clockwise so that you could give a 4 to this methyl group rather than a 5. So then, after you've figured either your longest chain or you've counted the carbons in your ring, you've assigned numbers, you figure out what substituents you have left over, you list them alphabetically. Again, commas to separate numbers, hyphens or dashes to separate letters from numbers. And you will use a number to indicate the position of the double or triple bond in the chain. So let's look at a couple examples of alkenes and see if we can try naming them. The process would be exactly the same for an alkyne, and just instead of having an ENE at the end of the name, we would have a YNE. So step 1, looking at letter A here, is figuring out what is our longest continuous carbon chain. So I'm just going to count straight across, 1, 2, 3, 4, 5. 5 carbons, 1, 2, 3, 4. Right, so it looks like straight across is going to be our longest carbon chain that contains that double bond over here on the end. All right, so quickly sketching in, this would be 1 then, carbon 2, carbon 3, carbon 4, and carbon 5. So our parent name here is going to be 5 carbons is pent, so we're going to have a pentene molecule. All right, so looking at our molecule then, if this is our main chain, right, the only thing we have hanging off here then is a methyl group off of carbon 3. So we end up with a 3-methyl, right, and then we need to put a 1 dash in here for 1 pentene to indicate where the position of the double bond is. Now if the 1 wasn't there, if it just said 3-methylpentene, you would assume it would imply to the reader that the double bond was in the 1 position. So let's try B here. Remember step 1, find the longest continuous carbon chain. Well, in this case it's not a branched alkene, so we only have one possibility straight across here. We count the carbons, 1, 2, 3, 4. Remember 4 carbons is bute, so this is going to be going to get the prefix bute. We should also look though and note that yes, our chain contained double bonds, and we actually have 2 double bonds, right, here and here. So this is not going to be just butene. This is going to be butadiene. Right? So if there are 2 double bonds, it becomes a diene. If there are 3 double bonds, it becomes a triene. You should not see more than 3. So diene, triene, if there's 2 or 3 double bonds. So now we need to number them so that our double bonds get the lowest possible number. The molecule is symmetrical, so it's not going to matter if we go left to right or right to left. So I'm just going to say 1, 2, 3, 4, because we need to indicate the position of the double bonds. Okay? So when you're trying to number double bonds, always give them the lower number of the 2. Right? What I mean is when you're looking at this, right, this is a 1, 2 double bond, and this one is a 3, 4 double bond. The number that I would write down would be a 1, 3 butadiene. Right? I don't say a 1, 2 or a 2, 2, 4. I give the lowest numbers here. So I have a 1, 3 dash butadiene. It tells you that you have a butane molecule. Right? So 4 carbons. I'm going to have 2 double bonds. One's at carbon 1 and one's at carbon 3. Now one thing about alkenes and alkynes that's slightly different than alkanes deals with their shape. So these molecules end up being much more extended, much more linear than alkanes because you have this rigid double bond here. So you remember when we were talking about alkanes and we said that you could spin about that carbon-carbon bond and come up with different conformers. Well, a double bond, right, is fixed. It's rigid. You cannot spin around this bond. So if you have an alkene and you end up with 4 different groups, right? This is only true for alkenes. It doesn't apply to alkynes. You end up with 4 different groups around that carbon-carbon double bond. Whatever side of the molecule they're on, you can think of this as being a fixed plane. A and E are on this side, and B and D are on this side. There's no spinning about this bond to change that. So these alkenes have particular ends and sides because they're rigid. So because of that, we end up in alkenes with something called cis-trans isomerism. So cis-trans isomerism only happens whenever an alkene has 2 different substituent groups on each of its ends, right? Meaning on this end, right, if this is an end and this is an end, right, we have to have 2 different groups here and 2 different groups here, right? Now these can match. One of these can be the same as somebody on the other side, but on this side, they have to have 2 different groups. So if you draw a line straight across an alkene, if these 2 groups are different and these 2 groups are different, and you draw a line across the alkene, if 2 of the groups end up on the same side of the double bond, right? So in this instance, I have 2 methyl groups on one side of the double bond. We say that those groups are cis, meaning they're on the same side of the double bond. If the 2 groups end up on opposite sides of the double bond, they're across the double bond, this being the line of the double bond, they're across the double bond, and we say that those 2 groups are trans. Right, so again, in order for cis-trans isomerism to be possible, you have to have 2 different groups on one end of the alkene. So in this example up here, right, on this carbon, I have 2 hydrogens, right, so cis-trans isomerization is not going to be possible. But on the molecule below, I have this double bond, and looking on either end of the double bond, on one side I have a CH2, CH3, and a hydrogen. On the other side I have a hydrogen and a methyl group. Right, so I have 2 different things on either end. These hydrogens match if we put these hydrogens on the same side of the double bond. Right now, cutting a line across this double bond, this is a cis isomer. If we take the same compound, but we twist it now, right? And this isn't possible to go from one to the other because this is rigid, right? But if in your mind you twist it, you end up with the trans isomer. So this would be trans to pentene, right? So these are 2 completely different compounds. You can't convert from one to the other. So let's take a look at a couple of examples here quickly. Up here in A, we have a compound. Let's say we have an alkene. Right? Let's say we want to name this compound. Right? Again, the process is the same. You're looking at the alkene, finding the longest chain. In this case, I have only 2 carbons. Not too hard to find the longest chain. So that's going to be eth is 2 carbons, right? So it's going to end in ene, ethene. Then I look and I see what kinds of substituents I have. So I have 2 bromos here, one on carbon 1, one on carbon 2. So I have, I'm running out of room here, I have 1,2 dibromoethene. And again, this would be all one word. I just ran out of space. The next thing that I have to do then, my one added level of complexity for these alkenes is to look and see, do I have the possibility of a cis-trans isomer here? And do I need to indicate that in the name? So when I look across this double bond, right, looking at one end, I have an H and a Br. Looking at the other end, I have an H and a Br. So I have 2 different groups on either end here. So I do have the possibility of a cis-trans isomer. So when I cut this in half and I look at this side, these hydrogens are on the same side of the molecule. Being on the same side means that that is cis. So this is going to be cis, we put it right out in front, cis 1,2-dibromoethene. So when I go to B here and I try to name molecule B here. Again, I want to find the longest chain that includes my double bond. So looking there, I'm going to go 1, 2, 3, 4. So my longest chain is 4. That's butene. Then I look at the butene and I see if I have any substituents on it. Right, so I have a couple of possibilities for numbering. I could number the butene 1, 2, 3, 4, or I could number it 1, 2, 3, 4. Either way, the double bond is going to get 2, 3, right? So if I go this way, it's 2, 3, or if I go this way, it's 2, 3. So the double bond's going to get a 2. If I go right to left, this methyl group that's going to end up being a substituent gets a 2. If I go left to right here, it ends up with a 3. So I'm going to go right to left to give my double bond the lowest number and my substituent the lowest number. So this is going to be thinking about my substituents here. It's going to be a 2 methyl dash 2 dash butene. So I've named the compound. Now I need to look at the compound and see, do I have a possibility of cis-trans isomers? Do I need to indicate that? So looking at the molecule, right, I have 2 of the same groups on this side, right? So I have no possibility for cis-trans isomerization. So chemical properties of alkenes. Alkenes are a lot like alkanes and alkynes, a lot like alkanes. They're nonpolar. We're still in the all carbon hydrogen realm. Soluble in organic solvents. They're less dense than water. When you put an organic solvent into water, it's going to float on the top. These are flammable. These guys are usually non-toxic. Again, alkenes can have cis-trans isomerization, and one of the things that we'll see, unlike alkanes, where there was only a couple of reactions that you could do with an alkane. You could burn it, or you could substitute one of the hydrogens for halogen. These alkenes and alkynes are very chemically reactive at the double or the triple bond. So I want to talk really quickly about different kinds of chemical reactions that are possible, not specific to alkenes or alkynes, just different categories of chemical reactions that we're going to see with alkenes and alkynes and with a whole host of other molecules in 102. So the first kind of organic reaction is what we call an addition reaction. Right? This happens if you have a double or a triple bond. We're going to look at this a lot here at the end of chapter 13. And what happens is you take an alkene or an alkyne, you take another molecule, and you simply add the atoms of that other molecule across the double bond. Right? In that instance, the double bond goes away, right? Because carbon can only form 4 bonds. So if you're adding something new on either side, you have to lose a bond. Same thing with an alkyne. You start with a triple bond. You have to add 2 molecules now. You can go from triple to double all the way down to a single bond. Our next type of organic reaction is what we call an elimination reaction. It's the opposite of an addition reaction. Now we're starting with what we got as the product of our addition reaction. We can eliminate the X and the Y here to get back to our double bond. And we'll look at this reaction as well later on in the semester. Our next type of reaction is a substitution reaction. This is the kind of reaction that we saw alkanes undergo. You're substituting a hydrogen for some other alkyl to make an alkyl halide. You're substituting a hydrogen for a halide. So in this substitution reaction, you have reactants that exchange parts, right? So maybe you have something AB that reacts with C, and you're going to swap the B and the C. So for instance, if you had this alkyl halide here, you could react it with this molecule, and you could swap the chlorine on the end of the molecule for the OCH3 on the other end. We won't look at these reactions this semester, but we will encounter them next semester. And our last type of reaction, which again, I don't think we will encounter this semester, is a rearrangement reaction, where your molecule doesn't change the number and kinds of atoms that it has. They just get rearranged to different places on the molecule. And so one example of this is if you started with a cis alkene, right, you could, under the conditions of, under acidic conditions with a catalyst, you could get it to convert to its trans form. So you've rearranged the molecules here, but you still have the same number and kinds of atoms within the molecule.